We're going to be learning about stoichiometry. So stoichiometry studies the amount of substances that are involved in a reaction. So in a stoichiometry problem, you can be asked to find a lot of different things. So here I've written out some things that you might be asked to find. So if you want to pause the video here and write down these bullet points, that can be helpful. And the problem we're going to do today, we're going to go over a lot of these things. So let's get started. So we have 3.00 grams of aluminum sulfate solution reacts to 3.00 grams of calcium chlorate. So the first thing we want to do in any stoichiometry problem is our first step of balancing our equation. So first, I always like to write out what they give us in the problem. So I've done that here, and this will help us balance our equation by having what they've given us kind of written out in words first, and then we can write our balanced equation. So here's our balanced equation. We have 1 Al2 SO4 AQ plus 3 CaClO3 2AQ yields 2 AlClO3 3AQ plus 3 CaSO4 solid. So now that we've balanced our equation, the next thing that we need to do in our stoichiometry problem is determine our mole ratio. So in order to do that, we need to be looking to determine our mole ratio. What we do is we look at the coefficients in front of each of our compounds, and that is our mole ratio in our reaction. And I always like to write that underneath each of them and like circle them. And we're going to use this number later in our stoichiometry problem. So next, now that we have our ratio between each of our substances, we can find the moles. So in order to find moles, we're given grams in our problem. So if we want to go from grams to moles, we have to use the molar mass. So here I have calculated the molar masses of our substances, and I've just written them underneath them to help organize my problem. And in order to find molar mass of like a compound, all you do is find the molar mass of each element, and then you just add them all together. And make sure if there's like a subscript, you like multiply like you keep that into account. So like if there's 2 aluminums, you take the molar mass of aluminum and you multiply it by 2. And yeah, that's how you do the molar mass. And so now if we want to go from grams to moles, we do our dimensional analysis. And here are our mole values for aluminum sulfate and our calcium chlorate. And so now that we have our moles, after doing our conversion from grams to moles using dimensional analysis and molar mass, we can find our limiting reactant. So in order to find our limiting reactant, we need to compare the mole values between aluminum sulfate and calcium chlorate with their like corresponding mole ratios. So here we've written out the mole values of each of aluminum sulfate and calcium chlorate with respect to their mole ratio. So I have 0.0145 moles of calcium chlorate per the 3, which is the mole ratio. And then we have the same thing, so 0.00877 moles of aluminum sulfate over 1. So those are my ratios. And if we actually like do the division out to make it clearer of which one is bigger or smaller, we have 0.0048 calcium chlorate and then 0.00877 of aluminum sulfate. And our limiting reactant is it's always the substance that is has like the least amount of moles, because the least amount is it's the least amount that is required to complete the reaction. So in this case, the least amount of moles that is required to complete the reaction is calcium chlorate, as 0.0048 moles is less than 0.00877. So since this value right here is less than it, our limiting reactant is calcium chlorate. So now that we've determined our limiting reactant based on the mole values in comparison to their mole ratios, we can determine the excess amount of like the reactant in the equation. So we said that the limiting reactant is the least amount required to complete the reaction, and we said that was calcium chlorate. So if calcium chlorate is the least amount, aluminum sulfate had a bigger value of moles, so that means there's going to be excess of it. So in order to find that excess amount, if we take the 0.00877 moles of aluminum sulfate and subtract it by the 0.0048 moles of calcium chlorate, we can determine that there will be 0.00394 moles left over in the reaction. And we subtract by this number right here because the limiting reactant drives the whole entire reaction. So that's why we're subtracting by this number right here to determine the excess, because the limiting always drives the entire reaction. Okay, so now that we've determined the excess, the limiting, our mole ratio, we can actually put all of our products and reactants into moles based off of these mole ratios and the limiting reactant. So let's do that. So we know that our limiting reactant is the calcium chlorate, and we know that that number of moles of calcium chlorate is the 0.0145 moles. So based on that number and the fact that the limiting reactant drives the entire reaction, we can put all the reactants and products into moles based off of that limiting reactant. So we have our mole ratio of 1 to 3 to 2 to 3. So based off of that, we can put everything into moles. So we have 0.0048 moles, because if we take the limiting amount of moles and divide it by 3, we get it to the 1. And then we take this number, since now this is it, the limiting reactants number, essentially times 1. We can take that and times it by 2 to get the 0.0096 moles, and then times 3 is this. So essentially, when we put everything, all the reactants and products into moles, we're using that limiting reactant mole number and the mole ratios to get everything into moles based off of that limiting number, because it's driving the entire reaction. So now that we have done that, we want to draw our beaker based off of what would be in it off of the products. So we have our square here, and that's going to represent our beaker. And when we are drawing what's in our product side, we want to draw our solid, which is right here, and also this aqueous solution right here. So let's first look at our solid. So when we have a solid, we want to put that solid into grams. So we know there's the solid is CaSO4, and there's 0.0145 moles of CaSO4. And if we want to do our grams to mole conversion, we have our molar mass right here, and we do the conversion, and we find that there's 1.97 grams of CaSO4. So now that we have it in grams, the CaSO4 solid, we can then draw it in our beaker. And we drew it in, we wrote in the value in grams, and then I also put it in as moles. And you always have to write your units and like the chemical formula. And then you draw brackets around it and then little dots to represent that it's a solid. And you draw it on the bottom. Now that we've done our solid, let's look at what we would do for the AlClO3,3AQ. So since it's aqueous, we know that we could break an aqueous solution into its ions. So here is what the ions in this solution are going to look like based off of the fact that they are aqueous. They're aqueous, so they're going to be broken into ions. So first, let's look at the Al3 plus and the ClO3 1 minus. So this appears on our product side, and we know our limiting has a mole value when its ratio is 1 of 0.0048 moles. So if we're looking at the Al3 plus, because that's one of our ions, there's two of them based off of the 2 coefficient. So we want to take the 0.0048, multiply it by 2, and that's how we get this 0.0096 mole value for the Al3 plus, which appears right here. And secondly, for the ClO3 1 minus value, there's a 3 subscript, and then there's a 2 coefficient, so 3 times 2 is 6, so we're going to multiply this value here by 6, and that gets us our mole value of 0.0288 moles of ClO3 1 minus. So that's how we get those mole values for our ions on the periodic side right here. Now, there are 2 other ions in this solution, and you might be wondering where those are coming from. We said there were excess, there was going to be excess in our reaction, and the excess was of the aluminum sulfate right here. And while it's not on the product side and we're drawing a beaker of the product side, the excess we will draw in the beaker as they are ions and they are excess. So that's why we have these ions right here. And that's what they are representing. So, since it's the excess, we calculated the excess amount of moles earlier in the problem, so we're going to use that number of moles to do this calculation. So for the Al3 plus, there's a 2 subscript, so we multiply the excess amount of moles by 2, and that's how we get the 0.00788 moles of Al3 plus, and then we get for the SO4 2 minus, we multiply it by 4 as there's a 4 subscript, and that's how we get the 0.0145 1183 moles of SO4 2 minus. And that is how you would draw the beaker. And then once again, since our ions are in an aqueous solution, that means they're in water. So we drew little water molecules, and notice how the heads or the tails are facing them based off of their positive or negative ions. So now that we've drawn our beaker, the next thing we would do is find the molarity of the spectator ions. And molarity is moles over liters, or volume, which would be in liters. And in this problem, we're not given like a liter amount, so we're actually not going to find the molarity, but this is how you would do it, and you would only find the molarity of the spectator ions. We're going to skip that, and the next thing we're going to do is write the ionic equation. So when you write the ionic equation, you take any of the aqueous any of the substances that are in an aqueous state, and you break them up into their ions. So we've done that here. So we have our aluminum sulfate, our calcium chlorate, and our AlClO33. Everything is broken up into its ions. The only thing that did not get broken up into the ion is the 3CaSO4 solid, because it's a solid, it's not aqueous, so you cannot break it into its ion. So when you break something into its ion, notice it has a charge and it's also still aqueous. So note that as well. And next step is we're going to write the net ionic equation, which is it's very similar to the ionic equation, but you remove the spectator ions. Spectator ions are ions that appear on both the reactants and the product side of the equation. So I have written the spectator ions here on the bottom, just so you can see which ones they were. And the net ionic equation is here. And we've removed the spectator ions from it. Okay, so next we're going to find the percent yield, and percent yield is calculated by taking the actual value and dividing it by the theoretical value and multiplying it by 100, and you get the percent yield. So the actual value is 1.5 grams of product, and the theoretical one, or the one we calculated with the stoichiometry, was 1.97 grams of the solid. So we do 1.5 grams of the solid, which is the actual amount, and you divide it by the 1.97 grams, which we calculated based off our stoichiometry, multiply it by 100, we get 76% yield. Next, we're going to do percent error. And percent error is calculated by doing actual minus theoretical divided by theoretical multiplied by 100, and that's your percent error. So if we do 1.5 grams minus 1.97 grams divided by 1.97 grams, and that gets us 24% error. And one thing to note is that if you take your percent yield and you add it to your percent error, you should get 100%. So we look here, we did our 76 plus our 24, and we get 100. Yeah, so that's the end of our stoichiometry problem. I know that was a long one, usually not that long. We just did every possible thing you could be asked in it. I hope this video helped. Remember, with stoichiometry, it's really important that you understand your mole ratios and molar mass and all that fun stuff. So thanks for watching this video.